All right, hello again. Same problem, same picture. Hopefully y1 is still root x and y2 is still x over 3, because that is going to make this much easier. Um, part B says find the volume of the solid generated when R, this region here, is rotated about the vertical line x equals -1. So this is going to be one where, because it's a vertical line, which is going to be over here, x equals a number is always a vertical line. It's going to be like, this is my axis of rotation. And so I'm going to rotate this area right here around this line like this. It's going to spin around like, it's going to come out of the page and end up over here, and then spin through the back of the board and come back around. I don't know what that thing's going to look like. Maybe like some kind of decorative bowl you might have on a table or something, but it doesn't look very, it'll look a little weird because there'll be a hole in the middle of it. And so this is a situation where I have to do two things to get this problem right. Thing one, I have to remember that I'm going to be doing this thing with each of my radii is going to look like this. This is going to be like the smaller radius, and this is going to be the bigger radius. And when those lines are horizontal, I have to write them in terms of y. There's like this is going to be y as a function of x because my cross sections are horizontal and not vertical. So I got to be like, this is x equals 1. Or sorry, this is x equals the line x equals -1. And so if I want to figure out this distance, when I'm doing horizontal distances, I have to do the right curve minus the left curve. If this was one where I was spinning this thing around a horizontal line, I do top minus bottom to find the distance. But here I'm going to do right minus left to find the distance. So my like kind of conceptual thing is going to be from like A to B pi big R squared minus little r squared minus little r squared dy. And just pay attention to this, that because the cross sections here are, because I'm spinning this thing around a vertical line, everything has to be rewritten in terms of y. So these limits here are going to be smallest y to biggest y. This big R is going to be the larger of the right minus lefts, and this is going to be the smaller of the right minus lefts. And so the trick here is to rewrite this thing, and by this thing I mean to rewrite y1 as like x equals something, and to rewrite y2 as x equals something. So that's going to be step one. So if I write y equals root x, which is what this first curve is, if I solve this for x, I square both sides and I get x equals y squared. So another way to write this curve, right here, this guy, is x equals y squared. I can do something similar with the bottom one, where I write y equals x over 3. I solve that for x, I get x equals 3y. So y1, the curve we called y1 before is now x equals 3y, and the curve we called y2 before, the curve we called y1 is this one, x equals y squared, and the straight line is x equals 3y. So now I want to figure out how to write big R and little r. Talk about the limits in just a second, but big R is this longer line. I don't want you to mix up. This R stands for the region. But this larger radius here is going to be the right curve minus the left curve. The right curve is this straight line, which we said is x equals 3y. And the left curve is x equals -1. So I did the right curve, x equals 3y, minus the left curve, x equals -1. Then I square that because I'm doing pi r squared. Pi r squared. And that's going to give me the little circles. The pi r squareds are going to give me the slices, the circular slices that I would get if I cut this thing in half. If I slice this thing horizontally, I would get these little slices that look like circles. But because there's going to be a hole in it, I got to subtract these little slices. That's what this minus r of y squared is. I'm going to find small r by doing the same thing I did before, which is right minus left. So for little r in my picture, I can see that this is the right curve here, and this is the left curve. This one, the right-hand curve, is y equals root x. I'm going to subtract the left curve, which is, oh, I did that wrong. Got to write everything in terms of y. Try that again. So my right curve here, y1, is this, x equals y squared. And my left curve right here is x equals -1. So I did right minus left, and I squared it. This whole thing is dy. So I'm getting there. I would like to know the limits though. And since this is a dy integral, the limits are going to be from the smallest y to the biggest y. The smallest y is 0. That's right here. And then I'm going to move up until I get y equals 3. That's going to be my upper limit. So this one is going to be pi. I'm going to go from 0 to 3 of 3y plus 1 squared minus y squared plus 1 squared dy. And this is a kind of miserable integral. I mean, you could actually do this by hand. It wouldn't be that difficult. If you square this, you're just going to get a polynomial. And you square this, you're going to get a polynomial. It's going to be a bunch of powers of y, which you can just, you guys know how to use the integration power rule to do that. But you don't have to because this is a calculator question. So you just punch all the stuff into your calculator. Again, the way you guys use your calculator to do integrals, you just replace all the y's with x's and you'll get the same answer. Calculator doesn't care what variable you're using. And you'll end up with, I believe, 207 pi over 5. You could write that answer, or 130.061, which is what your calculator will tell you if you leave the pi on there, or you could do 0.016. Any one of those three answers will be legitimate and acceptable answers here. So just some things to remember. To find the r's, you're always doing right minus left, or top minus bottom. You do right minus left to find r if the r's are horizontal, and you do top minus bottom to find r if the r's are vertical. And that just depends on whether you're rotating around a vertical line or a horizontal line. That's how you do part B. We can talk about part C maybe in another video.